Okay guys, today we are doing geometric sequences. So in a previous math class you guys learned about arithmetic sequences. Today we're doing geometric, but let's do a real quick review of sequences. So we're going to process this definition real quick. And so any sequence in math is a set of numbers related by a common rule. And they all start with an initial term. So I'm going to put this up on the screen real quick. It's not in your notes, you're just going to pay attention. So here's a sequence that you might have already been familiar with. The first term is 7, the second term is 9, the third term is 11, and so on. And this means that the sequence keeps going, but we don't need to keep writing it. So what do you notice is the common rule? What's the pattern? So if you see I already put a +2 here, these are all increasing by 2. So the rule that we see going on right here is that we are adding 2. Well, we just need to be really careful too that we put start with f of 1 equals 7. So that's just a fancy way of saying the value of our first term is 7. Okay, so I'm not actually writing the equation right now, we're just practicing recognizing the pattern. Okay, so let's go to the next one. Let's see if you guys can pick up the pattern. -5 to -8 to -11. Oh my gosh, these are getting smaller and smaller. Or if you prefer, bigger in the negative direction, which is still smaller. But what is happening is that they're each going down by 3. So we would be subtracting 3. But because our first term isn't 0, right? The 0 term, our initial term is -5. We need to say start with f of 0 equals -5. So this is a good point right here to look at these differences. This sequence's initial term was 1. This sequence's initial term was 0. So sometimes they're 1, sometimes they're 0. They really can be any number, but for our context, they're usually either the first term or the 0 term, but we call that the initial term because it's the first term that we have. Okay, let's go ahead and see if we can figure out a rule for this one. So it goes from 3 to 4, which would be adding 1, and then from 4 to 6, which is not adding 1, it's adding 2. And then from 6 to 9 would be adding 3. So this is not the same kind of rule that we were seeing in the above examples. This rule right here, we are adding consecutive numbers each time. So we went +1, +2, +3. Can you guess what the next one would be? +4, right? So I'm not going to write the rule for that right there because it's a little bit wordy and I want to make sure we're good on time, but we're going to put start with f of 1 equals 3. Okay, and then this last little one right here is the kind that we're going to be focusing on today. This one in particular is a geometric sequence, which is the title of our notes. And if you're wondering what a geometric sequence is, it says the ratio of any term to the previous term is constant. So that is what defines a geometric sequence right here. The ratio of any term to its previous term is constant. So let's just look at this one with that in the back of our mind. So 1 to 4 would be adding 3, 4 to 16 would be adding 12, and 16 to 64 would be adding a bunch. So we're not looking at an adding pattern. Maybe you can see it, but we're multiplying. 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. So our rule is that we're multiplying by 4. And then in this particular case, we are starting with f of 0 equal to 1. Okay? Now, you're like, okay, I get that, I see that pattern, but how is that related to this where it says the ratio of any term to the previous term is constant? So any term, so we're going to start with the first term because you have to have the previous term. So the first term is f of 1 and the ratio means a fraction, and to its previous term, the previous term to the first term is the 0th term, would be 4 over 1, which equals 4. Okay, now let's do the next one. If I take the second term, what would be the previous term? It would be the first term. And what's that ratio? Well, the second term has a value of 16, the first term has a value of 4, so we get 4. All right, awesome. Next term, f of 3, and its previous term is f of 2. And then when I'm doing this, the value of the third term is 64, divided by the value of the second term is 16, and in our calculator, 64 divided by 16 gives us 4. So are you seeing that common ratio of 4? So we have two ways we can see it. We can either take a term and divide it by its previous term, or we can see the pattern in our list. So that's pretty awesome that we have two ways that we can see it. Okay, so now what we're going to move on to is writing the rules for these, and there's two different ways to write the rule. There's something called the explicit rule, and within the explicit rule we also have two different ways. So within the explicit rule, if our starting term, if our initial term is 0, we're going to use this guy right here. So this starts with n equal to 0. That's what this guy right here. And this guy starts with n equal to 1. Now, I just want to show you real quick how you can tell from a formula whether or not it starts with a 0 term or a 1 term. So from a formula, real quick, let me show you guys this sequence right here. Here is the sequence. It's definitely geometric because I'm multiplying by 2 each time to get to the next term. Here is the formula for it. Here is the explicit formula. 4 times 2 to the n. Now, do you notice how there's not a number right here like a -1? That's because technically there is a -0 to show that it's starting with the 0th term. But mathematicians are lazy and they're not going to put a 0th term. They're not going to put a -0 because it's just extra things to write when it means the same thing mathematically. Okay, let me show you another one that starts with a 1. So here is a sequence that we can clearly see. The first term is n equals 1. It has a value of 3. But when you go to look at the formula for this one, this is what the formula looks like. It has an n minus 1. So that number right there corresponds to its initial term right there. So that's what I mean about this right here. Okay, so that's the explicit formula. The next one is a recursive formula. So these are two different ways to describe your sequence. It's two different ways to write what the pattern equals. It's two different ways to write a formula for your pattern, and you're expected to know both. But I will tell you that you will get a formula sheet on your test for these, okay? So you just have to know how to apply your formulas. So for the recursive rule, this rule right here says take R, that's your common ratio, and multiply it by the preceding term. So this should make sense after everything we've just gone over when we talk about geometric sequences. So if I want to find a formula for this pattern right here, I would take R, which is 4, and in order to find the next term, I would multiply it by its previous term. So the way that you write that with the formula is if you want to find a term, you take the common ratio and multiply it by its previous term. And we definitely are going to have to talk about whether our initial value is 0 or 1, which we've already been practicing. So let me go back to one of these examples that we started with, which was this guy right here. And we have this sequence right here, which we've already identified as being a geometric sequence because you're multiplying each term by 2. And then I'm just going to fold this so I can get it all on the screen. Here is the explicit rule for this guy. So this is this stuff right here, right? F of n equals a to the r to the n. Look at this. These are going to be so easy for us because whatever number is in the parentheses that has the exponent is the number, the common ratio. That's r. Oh my goodness, the formula even says that's your r right there. And then whatever number is here is your a value. Oh my gosh, that's so cool. Now, what about this recursive rule? So we see the recursive rule on our paper right here. This is the recursive rule for this sequence. So we say f of n, and we take our r, and we already know our r is 2 from this guy right here, and then we multiply it by f of n minus 1. Look, you don't even have to change that. So for the recursive rule, the only thing you have to change is your r value. So you substitute that in, and we say that this rule is only going to work for n is greater than or equal to 1. And the reason why it's only going to work for n is greater than or equal to 1 is because 1 minus 1, when you plug in 1 here, is 0. So you can still find f of 0. If I said n is greater than or equal to 0, f of 0 minus 1 would be f of negative 1, and I don't have the negative 1 term. So when you're writing the rule for recursive sequences, you always are going to do one higher than your initial value, and then you write what your initial value is, just like we did over on the orange paper that we were dealing with. Okay, so that was a lengthy explanation, so I think we are good to go and start working on these problems and see what we need to do. Alrighty? So, the first problem on this paper says, write the explicit and recursive rules for a geometric sequence given a table of values. So, if we want to write the explicit rule, it's right up here. You guys can see it right there, or right here. Which one do we use? Well, since this one starts with the 0 term, we're going to use that rule. So the explicit, I'm skipping a little bit of room just in writing it down here because we're going to use this space for some work right here. So the rule is f of n equals a r to the n. And I know you guys are just going to think this is super easy, but I'm being very detailed. So in order to write this rule, I need a and I need r. That's what I need to plug in. So a equals your initial value. And if you didn't see that up above, right here, if you want to go back up and highlight, where a is the initial value and r is the common ratio. Okay? For some whole number n. That's just the number of terms or whatnot. Okay. So in order to find r, I already told you guys there's two ways. You either take the term and divide it by its previous term. So 6 divided by 3, which equals 2. Or, because you guys are so good, you notice the pattern. Times 2, times 2, times 2. This is the pattern of multiplying by 2, so that's r. Okay? So what's our r value? R equals 2, and what's our initial value? It has a value of 3. Okay, so I'm just going to rewrite this another way real quick just because I want to make sure it's really clear. Your initial value, which is called a, is f of 0 in this case. Why is it f of 0? Because that's my starting value. Okay. So now we're just going to go Speedy Gonzalez through this. Ready? So f of n equals a is 3, it's my starting value, times 2 to the n. And we're going to put parentheses around these because we want to show that the r value gets the exponent, but that 3 does not. Okay? It's that simple for the explicit rule. Let's move on to the recursive rule. Okay, for the recursive rule, we're looking up here now. Here's the recursive rule. F of n equals r times f of n minus 1. So, super easy. F of n, the only thing we have to plug on this one is our r value, which we said was 2. and then keep it fn minus 1, f of n minus 1. So this is just saying if you want to find your n term, you need to multiply it by its previous term. So that is what a recursive rule is. In math, recursive means like recursive, kind of like cycle back. In order to find the next term, you have to know the previous term. In an explicit rule, I don't need to know the previous term. If I want to know the 100th term, I just plug in 100 and do the math. Over here, if I want to know the 100th term, I plug in 100, but 100 minus 1 is 99, and I need to know f of 99. So I need to know the value of the 99th term, and I don't. So it's just another way to write the rule. However, recursive rules, even though you only have one thing to plug in, require a little bit of extra work. You have to say that n has to be greater than or equal to 1, and I explained this to you guys on that other card. You have to say n is greater than or equal to 1 so that when you plug in 1, whatever number you plug in here gives you that value right there, that n value. So whatever number this is, just add 1. So if you started with 1, the n would be 2. If you started with 2, the n would be greater than or equal to 3. Since we're starting with the 0, this has to be greater than or equal to 1. And then we have to say, and our initial value is equal to 3. So all of that goodness for the recursive rule. Okay? All right, let's pick up the pace a little bit. Oh my goodness, now we're trying to figure out what's going on, what this pattern is. So when you do this one, you guys can definitely do the math of f of 2 divided by f of 1, which is 1/5 divided by 1 over 25. Because we're dividing, we're going to copy dot flip. And then 5 goes into 5 once, 5 goes into 25. 1 times 5 divided by 1 is 5. So there's my r. But hello, let's look at the pattern here. If we're not digging the fractions here, then we can just go right here. Okay, so we're multiplying by 5. Even 1/5 times 5 is 1. And 1/25 times 5 is 1 over 5. It all follows the pattern. So if you wanted to just say, show me your work up here and write r equals 5, I'm so glad you're picking up the pattern, that's enough work for me. Okay, an explicit formula for this, f of n equals a r to the n minus 1. Why do we do n minus 1 this time when in this previous one we only did n? That all has to do with our starting term. We started with the first term, so it should be n minus 1. Technically, this guy right here we talked about is n minus 0, but again, mathematicians are lazy and they don't want to have to write extra, so we're just going to write n for that. Alright, let's plug and chug. F of n equals, I didn't say my starting values, so a equals f of 1, which equals 1 over 25. So before, my a value was f of 0 because that was my starting term, but that is not the case in this problem, and that's a-okay. We just are going to memorize it as initial value. So that is what my explicit formula looks like. Great. Let's do the recursive rule. So the recursive rule does not change if you're starting with the 0th term or the first term, so that's nice. It always stays the same. And once again, this is just coming from up above on the top of your paper, and you'll also have it on a little card for the test. So you just really need to know how to apply these. So on this particular one, we need to make sure we're plugging in r, which is the common ratio of 5. That's it. Make sure you don't plug in a there. That's definitely an r value. And then we have to say for n greater than or equal to and f of 1 equals 1 over 125. So whatever number you start with, this n is greater than or equal to will always be 1 bigger. So it's 2. Alright, moving on. So here's C, and we're like, uh-oh, do you guys notice a pattern? This is why it's always good to not just go, you know what, I'm just going to do this method where we multiply by 5 all the time. This is where it's good to make sure that you actually know what's going on. So a geometric sequence has a common ratio. So if we want to know R, we're going to take the value of the first term and divide it by the value of the term before it. So 0.4 divided by 0.1. So we're just going to use our calculator. 0.4 divided by 0.1, and we get 4. Okay, so we get R is equal to 4. Let's see if that works. So I'm just going to do some quick math. 0.1 times 4 gives me 0.4. Times 4 gives me 1.6. Times 4 gives me 6.4. All right, perfect. That is our common ratio. And our A value, which is our initial value, is f of 0 in this case, and it's 0.1. So let's go ahead and do explicit. Which rule are we going to use? The one on the left over here or the one on the right? Because this is starting with 0, we're using that one. So f of n equals a r to the n. F of n equals 0.1. R always goes in parentheses. And that is it right there. Now when we come to do the recursive, we are going to do r times f of n minus 1. Super easy because we just have to plug in our r. But then we have to make sure we state our initial value in f of 0. Once I see that that's 0, I know that that's 1. So it's always 1 higher, equals 0.1. Guys, look how fast we are at these. This is awesome. Okay, moving on to the next one, D. Let's see. What do you see? It looks like there's some pattern of 10 there. So you might think you're multiplying by 10, but that's not quite right. So let's fall back on our pattern. So this is f of 2 divided by f of 1, just because it's the second term divided by the first, since we don't have a 0 term. So that's going to be 1/10. And then our A value is going to be f of 1 this time, because that's our initial value, which equals 10. So then we're going to come down and write our explicit rule. And so our explicit rule is going to be, we're starting with the first term, so we just got to make sure that we choose the one that has the minus 1. And then we just plug it in. A is 10, R is 1/10, and then n minus 1. That's it. And then we do our recursive. So for our recursive rule, that one stays the same. It's R times the previous term, and the fancy math way of saying previous term is f of n minus 1. So our R value is 1/10 times f of n minus 1. Our initial value is 1, so I know this must be n is greater than or equal to 2, and that's 10. I kind of went around that backwards in a weird way, but it works. Okay, last example besides the one on the back says, given the explicit rule for a geometric sequence, use a table to generate values and draw the graph of the sequence. So look, they've already given us this rule right here, so we know based upon the rule that that 3 is our initial value and that 2 is our common ratio. So you can either do something like this, 3 times 2 to the 1 minus 1, where we're plugging 1 in. 1 minus 1 is 0. 2 to the 0 power is 1, because anything to the 0 power is 1, and then 3. Then we can go to our next one, 3 times 2 minus 1. 2 minus 1 is 1. 2 to the first power is 2, times 3 is 6. Then we can go to our third one, 3 times 2 times 3 minus 1. before I do this math, I just want to point out, guys, we figured out shortcuts. In order to go from this term to the next term, if it's geometric, you just multiply by the common ratio. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, and so on. And now we're just going to graph it. So when we graph it, we need to label our axes, and we're not going to label them X and Y. We're going to label them N, because those are the ones we're plugging in, and F of N. And then we're going to go, let's just do like the first 3 terms, because that goes up to 12, and I don't really want to graph more than 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, 1, 2, 3, 1, 2, 6, okay, and 9, just so that there's even scale, 1, 2, 3. So the way we graph these is we're literally just plotting points. And what you'll see is that these start to take on the shape of an exponential graph, which we'll be talking about later in the chapter. Okay, that's it for that guy. Let's flip it over and do our very last problem. Okay, use the recursive rule. Oh, it's recursive this time. Woohoo! For a geometric sequence, use a table to generate values and draw the graph of the sequence. Okay. So this tells us right here, f of 1 is 16. The directions also tell us to round your answers to 3 decimal places where necessary. So we definitely didn't need it on the first one. And if you can remember, that value right there is your R. So let's just take our calculator and do 16 times 0.25, and we'll get 4. And then, times 0.25, and we get 1. Times 0.25, and we get 0.25. Times 0.25, and we get 0.0625. So let's say 0.063, and the pattern keeps going. So we're going to make our table. We're going to go to 16 though. 4, 8, 12, 16. We have N and F of N, but before I start plotting these, you can plot these as I'm chatting here. Before I start plotting these, I just want to show you guys how to plug into the actual formula right here. So this formula only works when n is greater than or equal to 2. So I'm going to show you why. So if I try f of 1, and that would be 0.25 times f of 1 minus 1, which is weird, but we're going to be okay. F of 0. Look at your table. 0.25 times f of 0. Do you even have an f of 0? No. That's why your first number you can use has to be f of 2. So if you plug in f of 2, we have 0.25 times f of 2 minus 1. Don't go dropping that f. Like sometimes students do that. You have to leave it there. 2 minus 1 is 1 until you can plug in what is the value of f of 1. It's 16. And when I do 0.25 times 16 in the calculator, I get 4, which is exactly what I got for my second value when I just multiplied all these by 0.25, since that was my R value. Okay, so let's plot them really quick. 1, 2, 3, 4, 5. This is 16. When it's 2, it's 4. When it's 3, it's 1. 0.25. So this graph is also taking on the shape of an exponential, but this one would be exponential decay because it's getting smaller over time. And that is it for geometric sequences.